Let's begin by talking about powers and exponents. Here I have an expression 2 to the fifth. This expression here is called a power, and the way to interpret it is as repeated multiplication. So I'm going to take 2 times itself 5 times. So what I have is 5 factors of 2. Try to use that terminology correctly. Each one of these expressions, the 2's, that are being multiplied together is called a factor in this expression because it's something involving multiplication. The parts of the power that we have over here are called the exponent, the raised portion, telling you how many factors you have, and the base, the lower portion, which tells you what you're multiplying together. Let's think about what happens when we multiply powers that have the same base. So for example, if I have 2 cubed, 2 to the third, times 2 squared, or 2 to the 2, what do I do with those exponents? So if I write it out, I'll have 2 times itself with 3 factors, that's 2 cubed, and then another 2 factors, 2 times 2, and so all day I have 5 total factors because I had 3 here and 2 from this power here. So if I just add the exponents, 3 plus 2, that will count the number of total factors that I have, 2 to the fifth. So the general rule here is if I have a base, b to the mth power, and I multiply it by something else, b to the nth power, I just add the exponents together, b to the m plus n. This is an example of what I would call a law of exponents. So this is some formula that tells you how to work with expressions that are in exponential notation. What happens if that power is something other than a positive integer? So if I have 5 here, it means 5 factors. But if I start to think about other kinds of real numbers as the exponents, this definition starts to break down. It's just counting the number of factors. And the first place you might see that is when you think about 0 as the exponent. So for example, what should 2 to the 0 mean? Well, maybe you know the answer to it, but it's important that whatever we decide that 2 to the 0 represents, it probably should be consistent with this law of exponents above. So to illustrate that, if I was to take, say, 2 to the 0 and multiply it by 2 cubed, the law of exponents above tells me I should add the exponents. So I go 0 plus 3, and I get 2 to the 3, 2 cubed. So that's interesting because I took this kind of mysterious expression 2 to the 0 and I multiplied it by 2 cubed and it didn't change it. I still have 2 cubed. In fact, if I divided both sides now by 2 cubed, it would cancel out on both sides and I'd be left with 2 to the 0 on the left, and canceling I'd have 1 on the right. In other words, 2 to the 0 must be 1. That's really the only sensible thing that it could be if we expect it to behave according to the law of exponents above. Multiplying by 2 to the 0 didn't change it because 2 to the 0 is really just multiplying by 1. So in general, b to the 0 is defined to be 1. And a little bit of a philosophical issue here, but we're assuming that our b is non-zero here. Raising 0 to the 0th power is an expression that has a bit of mystery around it, and we're just going to avoid that issue in this discussion here. So I'm assuming that b is a non-zero real number. Okay, let's talk now about dividing powers together with the same base. We just talked about multiplication, now division. So for example, if I take 2 to the fifth and I divide it by 2 cubed, what should we do with those exponents? Well, let's write it out. It's 2 times itself with 5 factors. And I'm dividing by 2 cubed, which is 3 factors, 2 times 2. And any common factor would cancel out here, so 3 of the factors in the numerator would cancel with the 3 in the denominator. I started with 5, I'm going to lose 3, and so it's 2 to the 5 factors in the numerator, and I have to take away the 3 that I lose, so I need to subtract the exponent. And it'd be 2 to the 5 minus 3, or 2 squared. So the general rule here is if I'm dividing powers with the same base, b to the m over b to the n, I should subtract the exponents, b to the m minus n. Again, here I'm assuming that b is non-zero, and especially here I'd be dividing by something that would potentially be 0 otherwise. Okay, what would happen now if our exponent was, say, a negative integer, a negative whole number? So if I was to take a negative exponent, how should I interpret that? For example, what's 2 to the minus thirds? What should that mean? It's not clear how to take 2 and have negative 3 factors that you multiply together like we did with 2 to the fifth. So we need to define what this should mean. I would like it to be consistent with any previous law of exponents like the 3 that we've already seen. So how should we define it to be consistent to that? Well, minus 3 is the same as 0 minus 3. Putting 0 in front of that and doing subtraction from 0 doesn't change that exponent at all. And why would I be subtracting exponents like this? Well, it looks like the right-hand side of my law of exponents above, we might have interpreted it as coming from division of powers. So you can think of it as 2 to the 0 over 2 cubed. Well, 2 to the 0 is 1. We've defined that earlier, so it's 1 over 2 cubed. So it looks like we should interpret a negative exponent as meaning 1 over that value, the reciprocal of that value. B to the minus n will be defined as 1 over b to the n. And again, I'm assuming b is non-zero here, or I would certainly be dividing by 0 otherwise. Some special cases, if I think about b to the 1, this has a clear meaning. It just means one factor of what I'm multiplying together. So that would just be b itself. So b to the minus 1 would be 1 over b. And that value there is the reciprocal of the number b. Resist the temptation to call this the inverse of b. There are many kinds of inverses in mathematics. If you want to call it the inverse, it's really the multiplicative inverse, the inverse with respect to multiplication of real numbers. But I would rather prefer you to call it the reciprocal of that number to avoid any confusion about what you might mean by inverse. Let's now look at some examples. Let's evaluate some expressions involving powers. So let's take 3 to the minus 2 plus minus 3 squared. Make sure you observe the correct order of operations. Any power would be computed, anything in parentheses rather would be computed first. So here the minus 3 would be computed first and then squared because it's in parentheses. The exponents are computed next. There's no multiplication or division going on here, and then finally any addition or subtraction would be performed. So on the left-hand term, here I have 3 to the minus 2, that becomes 1 over 3 squared. And the second term is just taking minus 3 times itself, squaring minus 3. So I get 1 over 9 plus 9. The minuses, notice I have 2 minus signs, so they'll cancel out. I'll have plus 9. If you wanted to combine those into one term, you could find a common denominator here. Here I have a factor of 9 in the denominator, so I'll multiply this second term by 9 over 9. That's just multiplying by 1. It won't change the expression at all. And so I have 1/9, and then the second term is 81 over 9. And I did that so that they have the same denominator, so that I can add the numerators together into a single fraction, 82 over 9. If you wanted to, you could go to a calculator now and get an estimate of that value, and that would be approximately 9.11. I've done some rounding. So notice how here I've drawn like a little wiggly equal sign here to indicate that I did an approximation. Okay, let's look at the second example here. We'll take the same expressions, the same terms, but we'll multiply them together instead of addition now. One way to approach this is to observe that minus 3 has two factors of -1 in there. So it's 3 to the -2 times -1 squared. I'm just thinking of them separately, and then 3 squared. Because it's squared here, the -1s will cancel each other out. And you could do what we did a moment ago and write the 1 over 3 squared, the 3 to the negative 2 as 1/9. But why don't we just illustrate a different approach here? I'm multiplying powers with the same base, and so I can add the exponents together. When I do that, I get 3 to the 0, and we define 3 to the 0 to be 1. You may come up with a different order of calculating this, but as long as you observe order of operations and do the calculations and the laws of exponents appropriately, you'll get the same answer as me. Finally, let's do a third example involving some division here. I have 3 to the minus 2 times 3 to the 4th over 3 to the minus 5. Let's do the numerator first. I'm multiplying bases or powers with the same base, so I can add the exponents together. Minus 2 plus 4 gives me 2, so this is 3 squared. And then I'm dividing by 3 to the minus 5th. Now I'm dividing two numbers with the same base, so I can subtract the exponents. It's 2 minus negative 5. So division results in subtraction, and the other exponent really is negative already, so there's a double negative in here. I'll get 3 to the 2 plus 5, or 3 to the 7th. And go to a calculator now and take 3 to the 7th, and I get 2,187 for our final answer. Again, you might have done this in a different order, but as long as you're doing order of operations correctly and applying the laws of exponents, you and I will get the same result.